Hi everyone, I'm Ankur. I'm a student at the Ant Lab at Berkeley, and I'm giving this talk in place of Joey Gonzalez, who couldn't make it. So all of us work on this graph analytics system called Graphx, which is embedded in Spark, and that's what I'll be talking about today. Now, so graph structured data is common in analytics, as you've been hearing about. Here's an example of an analytics pipeline that someone might use. You might, for example, if you're analyzing Wikipedia, you might parse it, extract a link graph, maybe run PageRank, and get a table of the top 20 pages. Or you might extract a term document graph and infer the topics associated with each word. Or you could extract a user edit graph and find communities of Wikipedia editors. So let's look at one of these algorithms, maybe say PageRank. PageRank identifies well-connected vertices by iteratively updating each vertex's rank using a weighted sum of its neighbors' ranks and repeating that until convergence. So here's the rank that it updates, and it performs this weighted sum. And these ranks can be updated in parallel, which is one of the key things that I'll be talking about in this talk. So here's what one step of PageRank looks like for one vertex, just to show that this parallel model. So here, each edge, first of all, is weighted inversely to the out degree of the source vertex. That's to ensure fairness. And then the update operation looks at the neighborhood of the red vertex, for example, and performs that weighted sum, which yields its new PageRank. So here, it's gone from 1 to 3.65. And that same operation happens in parallel at all other vertices as well. Now, here's a few more graph algorithms. I'll go over this and two more. First, there's single source shortest path. So this finds the distance from each vertex in the graph to a particular source vertex, which is the red one. And we can find this in parallel by setting the source vertex to have distance 0, and then iteratively updating each vertex's distance to be one more than the minimum distance of its neighbors. So here, for example, if we're looking at one particular vertex as the center, each vertex here can do this update independently using its neighborhood. So here, that central vertex will receive its neighbor's current distances, and then take the minimum of those, and then add 1. So now it's 2. And then, so therefore that central vertex is 2 hops away from the source. And this process repeats until the distances have converged. All right, a third example, collaborative filtering, which is a technique for building recommender systems similar to Netflix and their movie recommendations. So here, if two users like a similar set of movies, then chances are they have similar tastes. And so when one of them likes a new movie, for example, the other might like it as well. And we can use this idea to recommend movies to users, and that involves an iterative process of alternating least squares, which we can represent as a matrix factorization, or equivalently as an algorithm on a bipartite graph. Now again, vertices only need access to their neighbors in each iteration. Here's the update formula. So each vertex only needs access to its neighbors, and therefore all these updates can run in parallel. Now finally, a final example. Suppose a social network wants to predict certain attributes of each user based on postings and relationships. So for example, if we wanted to infer the political views of each user, say liberal or conservative, then we could start with some priors that come from each user's postings and try and then infer the priors, and then try and propagate those beliefs, assuming that friends are likely to share political views. So there's a graph that comes from the structure of the social network, and then we would propagate the views across that graph. All right, so this forms a graphical model, and we can use an algorithm called the mean field approximation to find solutions by iteratively computing over vertex neighborhoods and updating the probability distribution at each vertex. So in each case, what this does is it estimates the likelihood that each user is liberal or conservative, and then and updates based on that. And each of these updates again access only the neighborhoods of each vertex and can run in parallel with each vertex. All right, so all of these algorithms have something in common, which is that their parallelism exploits the graph structure. In particular, graphs are parallel over vertex neighborhoods. Now, graph algorithms in general might have some centralized state, and they might have state on each vertex and edge. And so, for example, the PageRank of each page is some state at a vertex. The current best distance to the source is state. The user or movie's feature vector is state, and so is the probability of being liberal or conservative. Now, in each iteration, the update to a particular vertex's state depends only on its neighbor state from the previous iteration. And this common pattern is what enables each vertex to perform its update in parallel. Right, so here's an example of 2 parallel updates. All right, so in addition to those 4 algorithms that I described, this neighborhood-centric pattern of graph computation captures a variety of graph algorithms from machine learning, data mining, and graph analysis. And a variety of graph parallel systems have arisen to support this pattern. So there's Google's Pregel, Giraph, GraphLab, and even if you look the right way, other systems like combinatorial BLAS. These systems all expose specialized APIs that let users express computation in this way that fits the graph parallel pattern. And they also implement special optimizations to run much faster than general data parallel systems like MapReduce. All right, so first the specialized abstractions. A common API that these systems use is the Pregel abstraction, where users write vertex programs that run in parallel on each vertex and send messages to neighbors. For example, in the PageRank and Pregel, it consists of three steps. There's this first where each vertex receives messages, rank contributions from neighbors. Second, where the vertex updates its rank to incorporate the rank updates. And third, where each vertex sends back the rank updates to the neighbors for the next iteration. So this fits into a common pattern of computation called the bulk synchronous parallel model. And here, there are computation elements, which in the case of vertices, that compute and send messages to other elements. And at the end of each iteration, they all synchronize at a barrier and receive the sent messages, and then the next iteration begins. All right, so specialized systems are attractive not only because they provide a well-suited interface, but also because they're fast. They build indexes in memory and lay out the computation to exploit the structure of the input graph. That makes them much faster than performing the same operations using standard data parallel operators like MapReduce or SQL. Like joins or group bys in MapReduce or SQL. And so, for example, a general system like MapReduce might take, say, about 1,300 seconds to run PageRank on a medium-sized graph with 69 million edges. Whereas another similar general system like Spark maybe uses memory better, and so it's 4x faster. But a specialized graph system like GraphLab is 16x faster than even that. So this is the impact of specialization on performance. And here's an even more emphatic example where for triangle counting, which is more communication intensive, Hadoop, which is a general system, takes 400 minutes on a very large cluster, whereas GraphLab is much faster, actually 1,000x faster on a smaller cluster. But there's one shortcoming of these specialized systems, which is that real graph analytics involves multiple views of the same data, not just running these specialized graph algorithms. It involves viewing the same data both as graphs and as tables. And currently, we need separate systems to support each of these views. On the one side, there's general systems like Hadoop and Spark, which provide table-based analytics operations. And on the other side, there's specialized systems like GraphLab, Giraph, and Pregel, which operate on graphs. Now, having separate systems for each of these views causes 2 problems. First, it forces the user to learn, deploy, and manage multiple systems. And second, to share data between systems, it forces the user to move that data across network and file system boundaries, for example, by reading and writing it to HDFS. So you might, for example, take Wikipedia, put it in HDFS, process it using Hadoop, put it back, and then use GraphLab, which requires repeated loading and storing. And that also precludes different systems from sharing these identical indexes that they've built over the same data. All right, so the solution that we propose is Graphx. And Graphx introduces both a flexible API that can operate on both tables and graphs, and it also introduces a system to back that API that uses graph parallel techniques to be as fast as specialized systems. The key to this is that graphs and tables are views of the same data. And switching between those 2 views gives the user access to more appropriate operators, and it also hints to the system some ways to optimize the execution by giving it information about the semantics of the data. All right, so in particular, you can view a graph as two tables. A vertex table associating each vertex with a property, and an edge table associating each edge with a property. And this is how we embed graphs in a general system. So we in particular embedded Graphx into Spark, which is another project from the AMP lab, and that provides these table operations for us. And we introduced a set of graph operators to do things like viewing tabular data as graphs, viewing graphs as tables, and computing things like PageRank. And there are also some functions that just run the appropriate table operator on the vertices or edges, things like map and join. So to summarize, Graphx is a library on Spark that allows viewing the same data as both tables and as graphs. And it provides a graph computation API that can express a variety of algorithms. And this enables all kinds of exploratory analysis to take place all from within the same system, Spark. Now let's go, next I'll go into some more detail on the abstraction that Graphx provides for working with graphs. So it provides two essential operators. There's triplets and MapReduce triplets. So triplets joins the vertices and edges and brings vertex properties to the edges where they're referenced. And then building on that, the MapReduce triplets operator uses the triplets to perform neighborhood computation as I described in the first part of the talk. So the neighborhood of a vertex is just the set of adjacent triplets, because the triplets also contain the neighboring vertex attributes. And so we can compute on neighborhoods by summing the triplets using map and reduce UDFs, which yields a new value for the central vertex. Here's an example of how this actually works. Suppose we're looking at the neighborhood of vertex A. We might look at just, maybe just the in edges, for example, or we could look at out edges or both. But the point is that here the map function would run on these triplets and produce some intermediate results. And the reduce function would sum the results of the map function, which yields a new value for A. And the idea is that this primitive can express a large variety of graph algorithms. Okay, so for example, we might try and find the age of the oldest follower for each user in a Twitter-like social network. And here we would take the age for each follower. So here's the code to do that. So here we would take the age for each follower, that's the e.source.age, and send it to the user being followed, which is the destination. And then we would take the maximum such age for each user, and this gives us the result. We can also use this primitive MapReduce triplets to express an enhanced version of the Pregel abstraction, which makes it easier to migrate to Graphx. And here's what that looks like. So the Pregel API it's a slight variant of the standard version, which separates out the vertex program, the message sender, and the combiner. And this separation makes it possible for Graphx to handle high-degree vertices in parallel on multiple machines. All right, so here's what it looks like to use Graphx end-to-end. If we were trying to write PageRank, for example, in Graphx, we would first load the graph and get the out degrees of each vertex just to set the edge weights. And then second, we would run Pregel with the three functions. So there's the vertex update function, the message sending function, and the combiner. And also we could give it things like initial message and number of iterations. And then and something to note here is that graphs are first-class objects within Graphx, meaning that you can have more than one at a time and pass them around like any other object. In contrast, specialized systems like GraphLab only let you operate on one graph at a time. All right, so graph computation in Graphx happens with the MapReduce triplets operator. So the implementation of Graphx focuses on making it fast, especially for iterative algorithms where it's called repeatedly and the graph is updated based on the result. All right, so Graphx, first of all, represents graphs as two distributed tables. There's the vertex table and the edge table. And vertices are stored as pairs of vertex ID and vertex attribute, and they're partitioned by vertex ID. And the edges are stored in a separate table, which implies a vertex cut layout, where a single vertex might have neighboring edges on multiple machines. This is in contrast to systems like Giraph or Pregel, but like GraphLab. So this lets the system balance high-degree vertices across machines without any problem, since we can just perform communication in parallel regardless of how many vertices there are connecting to a single, sorry, how many edges there are connecting to a single vertex. All right, now forming the triplets view, so here's the edge table. Now forming the triplets view from this requires a join between the vertex and edge table, meaning it requires that each vertex attribute is sent to the edge partitions where that attribute is referenced. And doing this join, it's difficult, and so we present an extra data structure. We use an extra data structure that facilitates the join by describing for each vertex attribute which edge partitions it should be sent to. So for example here, vertex A is mentioned by edges in both partitions, so to form the triplets view, it needs to be sent to both. Now once the vertex attributes have been sent to the edge partitions to form the triplets view, it makes sense to cache them there in case the user or future iterations need to access the triplets again. So we store the vertex attributes at a mirror cache of the edge partitions. All right, now finally, the way that MapReduce triplets actually works is by scanning the triplets on each edge, on each edge partition, and running the map function on each of those triplets. And those calls to the map function produce local aggregates, and then we can send the local aggregates back to the vertex table for final aggregation. All right, now we made 3 important optimizations to this pattern to make the core of Graphx faster. First, iterative algorithms typically update some of the vertex attributes in each iteration, only some, at least some. And so the mirror caches need to stay up to date to form the triplets correctly. So rather than rejoining all the attributes each time, we just update the caches incrementally. So if say, vertices A and E are changed, then we only move those across the network. And for some algorithms, this actually can result in a really large drop in communication and runtimes. So for example, for this algorithm connected components where the vertex attributes converge after a few iterations, the total communication drops by 5 orders of magnitude after the 8th iteration, because the values for most vertices have converged by then. Next, some algorithms only require one side of the triplet. For example, the rank update in PageRank only depends on the rank of the source vertex, not the destination. And for these kinds of algorithms, we actually can figure out which vertex is necessary, source or destination, and only ship that one. So here, vertices G and F aren't needed to run MapReduce triplets because they only appear in the destination position here, never in the source position. And so we therefore can avoid shipping those by inspecting the map UDF. And here's the performance impact of this. As you'd expect, it gives about a 2x reduction in communication since we can skip sending half of the vertex attributes in each join. And one interesting thing is that Graphx can actually can do this because Spark is written on the JVM, and so is Graphx therefore. Whereas GraphLab actually can't do this optimization at all because its UDFs are written in C++. All right, now the third optimization is that for many algorithms, we can figure out which edges the map UDF needs to run on rather than just running it on every edge. For example, in connected components, if none of an edge's neighboring vertices have changed components since the last iteration, there's no need to send a component update along that edge. So that means that certain algorithms, like connected components, have the concept of an active vertex set, and only edges adjacent to active vertices need to run. So we provided a way for applications to communicate this active vertex set to Graphx via MapReduce triplets, and then for algorithms where that set shrinks rapidly, that can give us a further opportunity, which is that rather than scanning every edge and checking whether it's adjacent to an active vertex, we can index the edges by vertex, and then just scan that index and filter it. And this saves us from having to touch maybe billions of edges in later iterations. So here, the runtime per iteration drops substantially in later iterations. And what we currently do is switch between a naive full scan and an index scan when the number of active vertices hits some threshold, so say 80%. Finally, there are also some other local optimizations that Graphx performs. For example, indexing within each vertex and edge partition. And index reuse as well. When the user transforms the graph's properties without modifying the graph structure, we're able to actually reuse certain indices as well as the routing table that was previously mentioned. And this avoids the cost of reindexing, and it also makes it fast to join the derived graph with the original graph, which is one of the interesting operations that Graphx provides. All right, finally, as a result of these optimizations, Graphx is actually, well, first of all, it's an order of magnitude faster than just naively writing, say, PageRank in Spark. And it's also comparable in performance to the fastest specialized graph systems like GraphLab. But it also provides much more flexibility due to being embedded in Spark. So here's a benchmark of a web crawl, of PageRank and components on this web crawl that has 3.7 billion edges. And here, Graphx actually is faster than GraphLab in one case, and it's comparable in general. Okay, so we've released Graphx as part of Spark 0.9 several months ago, and since then it started to be used in an encouraging manner in industry, and it's also been getting some open source contributions. All right, finally, there are several interesting directions for the Graphx project that we're looking at next. One of them is computation on time-varying graphs. So existing graph systems tend to focus on analytics on static graphs. But there's been a lot of work in academia about incremental graph algorithms that make it possible to efficiently accept updates to a graph. And we're interested in making it easy to express those, meaning making it easy to write an algorithm that is built on top of a graph, and then as that graph changes underneath, the changes can propagate through the algorithm in an efficient manner. Second, Graphx focuses on batch iterative graph computation, and so does GraphLab and so on. But there are also a separate category of efforts which are graph databases, like Titan. And these focus on graph storage and fast point queries. And these two roles are complementary, and so we're interested in providing a Titan-like interface over Graphx data. And finally, graphs might actually be stored in compressed format on disk. And it's worthwhile to explore how to operate on compressed graphs natively. And that actually takes advantage of one of the interesting properties of Graphx, which is that it doesn't require random access to the edges. I mentioned that its core operation is to scan edges and then access vertices randomly. And so it could actually support operating on compressed edge data on disk. All right, so that's all I have. Yeah, thanks.